Today we're going to be talking about FIR, which is the new cluster in the Alliance. So FIR is hosted and operated by Simon Fraser University within Canada's National Digital Research Infrastructure. So FIR, as you know, replaces the old CEDA cluster. And CEDA has been around for a while, since 2017, so it's been 8 years now, long due for a refresh. And FIR is now, so CEDA has been retired now, and FIR is open and available to all academic researchers in Canada, so as of August 12th. The name, it's named after the Douglas fir species, so continuing the tradition of naming big clusters at SFU after big trees in BC. And it's actually a lot more powerful than CEDA. We're looking at about 3 to 4 times increase in raw CPU computing power and memory. The number of GPUs actually went down because CEDA was refreshed several times over the past 8 years. And on CEDA, we had quite a mix of older and newish GPUs. So on FIR, all GPUs are H100s, the most recent commercially available generation of GPUs. And even though we don't have as many GPUs as on CEDA, they are so much faster than the total combined computing power in GPUs actually went up by a factor of 3.5. So preparing for this webinar, I did a lot of testing, and in my own tests, a single core on FIR is about 5.5 times faster than on CEDA, but that is probably problem dependent. So this number might differ, depending on your code. And then there's the famous top 500 list, which is published twice a year. So that's the list of the fastest supercomputers in the world, and it's published in June and then in November each year. And at the time when the list came out in June, so the team ran benchmarks on the partially assembled FIR, and it is now ranked at number 78, which is great. So we got into the top 100. But again, this was run just on the partial cluster, so during assembly, and it'll be very interesting to see how that number changes in November. So FIR is now open and ready. You need an Alliance account to get access to FIR. Actually, in a few minutes, I'll talk about getting access in more detail. But it's ready, and it's you can run general workloads. Simply have an account, and you can just log in and submit your jobs to regular queues, as well as it now fully supports RAG 2025 allocations. So since the cluster is very new, some services are not set up yet. I'll talk about these. There are quite a few of them. I'll talk about these and the estimated completion times during the webinar. So FIR is not the only system that is new in the Alliance. So we have quite a big round of hardware refresh over the past few months across the country. And so in this slide, you can see the systems that were replaced. So CEDA was replaced by FIR. Beluga in Montreal, in Calcul, Quebec, was replaced by the new cluster called Rockwell. Graham used to be a cluster at the University of Waterloo in SharkNet. Now it is NIBI, and Niagara at the University of Toronto SciNet was replaced by Trillium. So there's one old system, a legacy system that still stays around for the next couple of years. That's Narwhal cluster in Montreal, in Calcul, Quebec. And because that system is only a few years old, so it's going to be refreshed, I guess, replaced probably 2-3 years down the road. So if you look at the total number of CPUs, GPUs, etc., across the country on these systems, so we have more than 5,000 nodes, almost 800,000 CPU cores, and then more than 2,000 GPUs. So preparing for this webinar, I created this plot, and what it shows is, so it shows all the clusters, so the new clusters: FIR, NIBI, Trillium, Rockwell, and then Narwhal is the older cluster. And the size of each partition, so it's sized according to the maximum theoretical flop, so single precision floating point operations per second. And as you can see, because there are so many GPU nodes on CEDA, 160 GPU nodes, it's really heavily biased towards GPUs. So, for example, FIR is, the size of FIR is in terms of raw computing capability, well, theoretical computing capability, is actually bigger than the size of Trillium, which is the University of Toronto. But this is, this is just based on the fact that here we are sizing everything by the maximum theoretical performance. So real-time performance will depend on the code, and of course, it's not going to be as heavily biased towards GPUs as in this plot. So real-time performance will probably be, it will depend essentially on the code. So for some applications, if you run a code on, let's say, the whole of Trillium and compare it to the speed of the whole of Fur, Trillium might actually be faster. And then the color here represents the number of GPUs per node. Actually, let me zoom out a little bit so I can click on the links. And I'm going to show you the interactive version of this plot. So here we have Fur, and if I click on Fur, then here you can see the three main partitions. So there is the base partition with 864 nodes. These are CPU-only nodes. There are 160 GPU nodes with 4 H100 GPUs per node. And then there are also large memory nodes, which here are, because everything is sized according to flops and GPUs clearly win. This is the large memory partition, which has only 8 nodes, and that's why it's so tiny. But as you can see, all new clusters have GPU partitions as well. So, for example, at the University of Toronto, Niagara didn't have any GPU partitions, so now Trillium has 60 GPU nodes and so on. So all of these clusters are available to everybody across the country. So once you have an Alliance account, you can simply log in and start computing, or you can apply for a RAC allocation in the fall, so that that competition is coming up very soon. So Fur, NIBI, Rockwell, Narwhal are general purpose clusters, which means that you can run pretty much any computational workloads on them. So you can do serial farming, launch a lot of serial jobs. You can do small scale parallel codes. You can do large scale parallel codes, etc. So Trillium is different. So continuing the transition from Niagara, Trillium only accepts large parallel jobs. So scheduling there is by a node, which means that each node has 192 cores. So that means that you have to schedule jobs in multiples of 192 cores. So as I mentioned, all GPUs on the new clusters are NVIDIA's H100 cards. I'll talk in more detail and how it will affect scheduling soon. So the software environment is mostly identical on these clusters. All of them load the standard environment 2023 standard environment from the Alliance. But there are some differences, of course, as well. So job sizes, maximum run times, file system specifications, quotas, policies, and services offered might actually differ from one cluster to another cluster. So to get access to Fur, you need a compute, sorry, not a compute kind of, now the Alliance account. So to apply for an Alliance account, you can find links in many places. I assume that most of you, since you already attend this webinar, you already have an account. But if you don't, you can simply go to the documentation, and then I'll paste the link to the documentation into the chat. And then here is a link to get an account, right? Getting an account right here. So you need a single Alliance account, and that will give you access to all systems. Once you have an account, you will need to go to CCDB, so this website, or you can alternatively simply enter CCDB into Google search, and then you will log in with your Alliance account, and then select resources, access systems. And then you will see a graph, well, a page similar to this one. So if you have used CEDA recently in the past few months, we automatically give you access to Fur. If you have not used CEDA for a while and you have never used Fur, then you will need to click on request access. And as far as I know, right now you don't have to agree to any forms, so you just request access. You agree to some forms when you applied for the Alliance account. But other systems, for example, Rockwell, a few others, that might actually require you to accept some forms, some terms of agreements and policies as well. So once you click this button, it might take up to 1 hour for access to be enabled, and then you will be able to log in via SSH. So SSH access is the same as it used to be on CEDA. So you will simply SSH to, in my case, my username is Razumov, and then it's at furalliancecan.ca. And then, of course, it will ask you for double factor authentication, which let me just enable it here. So I will log in. So to set up double or multiple factor authentication, we have all that described in the documentation. So hopefully most of you are already set up. So once you log in, you will find yourself on one of the login nodes. There are currently 3 login nodes at the moment. That number might grow a little bit in the future, but basically you randomly land on one of the login nodes, and these nodes have pretty much the same limits on user processes as on CEDA. So you cannot launch too many processes, you cannot use too much memory, etc., etc. So this slide shows the system highlights. We have 175,000 cores, CPU cores on Thur, and then there are 640 GPUs. So the base nodes already mentioned, there are 864 base CPU-only nodes. Each node has 192 cores and then 750 gigabytes memory, and it's all AMD-based. So if you divide the amount of memory by the number of cores, you will get the familiar ratio of roughly 4 gigabyte per core. So that's the same as on CEDA, and that makes it really, really easy to submit your jobs, because essentially it's going to be very, very similar environment to CEDA. There are also 8 large memory nodes with 192 cores and up to 6 terabytes of memory. And these will be useful to researchers who run multi-threaded applications that require a lot of memory. So GPU nodes, 160 GPU nodes, 48 cores, 1100 gigabytes of memory, also AMD-based, and each node contains 4 NVIDIA H100 cards. 51 petabytes of elastic storage partitioned into three parts: home, scratch, and project. All nodes are connected by InfiniBand NDR Fabric interconnect. The operating system is Alma Linux 9.6, which means that you have, well, like any HPC cluster, you have to be familiar with Linux command line, and we regularly teach courses, introductory courses to Linux in Bash and introduction to HPC throughout the year. So if you are new, for example, if you're a new student and you don't have any experience with Linux or HPC, please consider attending our courses, because there's quite a lot of things to learn. So on the nodes, there is direct-to-chip liquid cooling, which is supposed to be quite efficient, a lot more efficient in terms of power usage compared to CEDA. And then both login nodes and compute nodes have full access to the internet. So this is actually an exception compared to the other clusters in the lines. So as far as I know, CEDA is, I might be mistaken, but I'm pretty much sure that CEDA is the only cluster that allows internet access from the compute nodes. All right, so in terms of file systems, I already, yes, so the slides, let me paste the link to the slides into the chat. The slides are available, and you can find them by going to this page and then getting started. And then the first webinar, if you click on it, it will expand and we'll see the link to the slides. So already mentioned elastic storage. So we have the large 51 petabyte storage system attached to the cluster. So it's all SSD based now. There are no spinning drives. And it's the same elastic storage is shared by 3 mount points. So there's home, there's scratch, and there's project. So the setup is very, very similar to what we had on CEDA, except that on CEDA, it was 3 different physical file systems. Now it's the same file system, just split into 3 parts with different quotas and different policies. So there's still no automatic compression and deduplication. So keep in mind that if you have any large files, then you might want to consider compressing them or packing them into archive and then compressing these archives. By default, when you log into the cluster, you will find yourself in home, which has a 50 gigabyte quota. So it's a very small quota meant just for storing your codes, your text files, your input files, but there's no purge policy. So your files can stay there pretty much indefinitely as long as you are below your quota. So to find Scratch and to project, you can either follow the symbolic links in your home directory, or there are also variables, Scratch and project variables. So let me just show this to you. So if you display Scratch, you'll see that it will just point to a Scratch directory. And if I go there, right, and then if I do pwd -p, it will show that now I am on Scratch partition. So notice the Scratch /Scratch will have a large number of users, I don't know, 10,000, 15,000 users. So I don't recommend going directly into /Scratch, but that's why we have this variable that is conveniently pointing to the exact location of your own Scratch directory. And if I go back into home, there's also a Scratch. I believe it's a link. Yes, a Scratch link in your home folder that's also pointing to your own Scratch directory. So for projects, there is a project variable, but this variable points to your default Scratch directory. And some people might have multiple Scratch projects. So I prefer to use the projects directory. So that is a usual directory in a home. And then if I do ls-l inside this directory, you will see that it points to all your project allocations. And so here, for example, my usual project allocation, then if I go in there, you will see that it's a directory where it belongs to, well, API. So the person who, under whose account this this project directory was created. But then if there are multiple users inside your research group, these users will have their own subdirectories inside that project directory. There's a question, do we need to accept any new policy for using it? So as far as I know, no. As far as I know, going from CEDA to FER, you don't need to accept any new policies. At least as of a couple of weeks ago, when I went through this process, I didn't have to accept any policies. Another question: do you have plans to increase the number of file I/O operations Lustre can handle across those 3 partitions? Great question, and I don't really know the answer. So I will ask the admins. I don't really know because the cluster is currently still being essentially assembled. A lot of services don't work. I'm sure they will look into this, but I don't know the answer. Yeah, file I/O performance was a significant challenge on CEDA. So can you comment on how this will be different on FER? So the new Lustre file system on FER is brand new. It's much newer than the older Lustre file system or file systems on CEDA. So it's supposed to be performing much better. That's all I can say. So it's newer. The failure rate is supposed to be much smaller because it's all new hardware. So the problem with CEDA was because the system was essentially 8 years old. A lot of hard drives were just physically failing, and that led to a lot of problems. So the new system should be faster, but in terms of adjusting it for file I/O, I don't know. So one thing that you can always do, you can use local scratch. So I have a slide for that. So it's the same system as on CEDA. There is a local scratch disk attached. Well, there's a local SSD attached to each compute node. And then on CEDA, it was pretty small. It was, I think, 2 terabytes or 1 terabyte, something like this. So now it's 7.8. It's more than 7 terabytes on FER, which means that you now have a lot access. Well, you have access to a very large pool of a very large local disk space, which is fantastic for large file I/O if you do frequent reads and writes. What is the maximum wall time? So I'm gonna talk about this in a few minutes. All right, so every group has a project. So Scratch, yeah, we're going back to Scratch. So Scratch directory has a very similar purge policy to CEDA. So we're following the alliance's procedure. And essentially, every user has roughly 20 terabyte quota in Scratch. But if everybody starts filling their quota, then of course we'll run out quickly of this space. So to mitigate this problem, we have a purge policy in which all the files will be deleted. So on average, it's 6 weeks, might be longer, a little bit longer, maybe 8 weeks, so depending on how fast Scratch is filling up. We'll send you, of course, several email warnings before we actually delete your files, but just be aware that there is a purge policy on Scratch, so same as on CEDA. So each group has a 1 terabyte quota in project, so very similar to CEDA. What is different is that now the quota is computed differently. So on CEDA, it was based on the file group ID. So now it is it is completely independent of the group ID or the file group ID or the file user ID. So essentially the file ownership. Essentially any file that is physically placed into one of the subdirectories in a project directory will be counting towards the quota. And this actually solves a lot of problems when people in the past try to move a file, let's say from Scratch into project, and they got wrong permissions because the default permissions on Scratch and project were different. So now all these problems are gone, right? So you don't have to worry about quotas or permissions because everything is computed automatically. So to request an increase in your project space, ideally, you should do it via RAC. So again, every fall in November, October, November, we'll have the competition. So you can ask for a larger project petition. But we can also temporarily increase your regular non-RAC allocation in a project as well. So the quotas, same system as before. So you can use the disk usage report command or the quota command, which is essentially an alias for disk usage report. So you can do things like quota dash dash and then the file system. So here I'm looking at my usage in home. As you can see, I'm almost full in terms of disk space, and number of files is the same as in CEDA. So 500,000 files in your home directory. So if you want to see usage for all partitions, you can simply say quota without any flags, and that will give you usage in home scratch project and nearline. So in terms of data migration, all data has already been moved from CEDA to FIR, so you don't have to do anything because the two clusters actually share the same mount points for Lustre for quite a while, and all migration should have happened automatically a few months ago. So for file transfer, now please use the login node. So there's a plan for a dedicated data transfer node, but it's currently not there yet. It should be coming online in the next couple of months, I think. And then for Globus endpoint, it's just align scan hashtag FIR-Globus. So once you log into the Globus, let's say, website, into the Globus interface, search for FIR, and then once you see this endpoint, that will give you access to the FIR file system inside Globus tool. So local scratch, already quickly mentioned it. There is 7+ terabyte SSD attached to each compute node. And then to use it, you'll have to start a job. And depending on which node your job will start running, you will get access to a directory which has the following name, right? So it's right here, this one, which is stored as slurm-tmp directory variable inside your job. So the only thing is, so you can write lots of small files there. You can read a lot of small files, so fantastic performance will be fantastic. But just make sure that you copy all data out before your job ends. Otherwise, your data will be lost because it's just a temporary directory. TMP/TMP, both on login nodes and compute nodes, is a RAM disk that you can use. But those files and directories that are put into RAM disk will essentially be gone the next time the system is going to be rebooted. Or that usage also counts towards your C group limits, and so memory usage limits. And at some point, you will simply not be able to use TMP if you dump a lot of files in there. So nearline, very similar. I mean, actually, it's exactly the same nearline system as on CEDA. So there's no new hardware. The entire tape storage was physically moved from CEDA to FIR. So by default, it is available to PIs only, but of course, users can also get access to it through their PIs. As usual, I use tar or DAR, disk archiver commands to create an archive directly in nearline. So here's an example. Let's say I have a directory in which I cd into a directory where I have a lot of data files, and then it's just some numerical simulation from a previous visualization competition. And then here I have, I use DAR, disk archiver, to create 10 gigabyte slices that I put directly into nearline directory, right? And so this will take a while. And then at the end, I also create an index. And the reason I want to create an index, even though DIR tool also includes an index into the archive itself, is because index will not be moved to tape. It's just a permanent, essentially permanent. It will not be deleted from disk, a file that you can use to check quickly where your files are on tape, right? Okay, so networking. The base CPU only nodes are grouped into 4 islands. For communication between the islands, there is a blocking factor. I don't know. I tried to look up the speed of the InfiniBand India connect between the islands, and I don't really have a single answer. But remember that there's a blocking factor in the sense that if you try to saturate the network between the islands, then there will be some blocking. So it will saturate at 5/27th of maximum theoretical speed because there is a limit on the bandwidth. And then, so there are 4 islands, and then inside each island, the nodes are grouped into 108 trays. There are 2 nodes per tray, and then there is a single 200 gigabits per second going into the first node in each tray, and with another follow-up cable going to the second node. So what this means is that essentially inside each island, every pair of nodes are guaranteed to have at least 100 gigabit per second connection to each other. and then it might be actually as fast, so depending on where these nodes are, it might be actually as fast as 200 gigabits per second. So the GPU nodes utilize a 2x1 blocking factor for communication between the islands, and then storage access is fully non-blocking. There's a question, can we continue to log into CEDA if we are only working on organizing files? The answer is no, I don't think so. So CEDA has been decommissioned, and unless CEDA.alliancescan.c points reroutes automatically to FIR, I have not tested this. You should not, I mean, CEDA is not available. So FIR is the cluster where all your files are. So if you have any files on CEDA, all those files have been moved to FIR. So please log into FIR. So in terms of software, it's essentially the same as on CEDA. So there's not much change. The standard environment 2023 is now default, but all the environments like 2020 are still available, but they're hidden. So you have to search for them looking at module avail command. CUDA 12.6 is now default on all new national clusters. If you go from CEDA to FIR, you probably want to recompile your code because the executable might not work. The executable that you created on CEDA might not work on FIR. And you also want to redo the scalability test of your parallel CPU code simply because things are somewhat different on FIR. So I'm going to talk about it in the next few slides. You also might want to reinstall your Python virtual environments because the paths might have changed and some things have moved on FIR compared to CEDA. So the very first time I logged into FIR, it actually complained about an old Intel module, and I think that might have happened. I don't have anything in my .bashrc file or .bash profile file, but I think that happened probably because at some point in the past I saved a module configuration, and then all I needed to do in this case, if you see a complaint about an old module not being available, I just do module reset, and that should reset your modules. So the scheduler doesn't have any new features. Maximum job runtime is now 7 days. So on CEDA, it used to be 28 days. Now on FIR, it's 7 days. So job runtimes range from, actually, there's a mistake, not from 1 hour, but from 3 hours to 7 days. So yesterday, I looked into the runtimes and the number of nodes per each partition, Slurm partition for different runtimes. And this is the plot I came up with. So as you can see, the number of nodes is, so the highest number of nodes is in the 12-hour partition, and then you can submit jobs up to 7 days maximum. So jobs longer than 7 days are no longer allowed, and that's a uniform policy across the federation. So let's go into the nodes and talk about scheduling scheduling on best scheduling inside on nodes for best memory allocation. So if we turn to the base CPU partition, 864 nodes, so each node has 192 cores and 750 gigabytes of memory. So physically, these cores are sitting on 2 sockets with 96 CPU cores each, and then each socket is organized into 12 chiplets. So like think of them as small partitions on a socket. And then, so there are eight cores inside each chiplet. And also each chiplet is a separate NUMA node. So NUMA stands for non-uniform memory access node. So that means that all cores on the same chiplet shared memory, the same bandwidth, the same network to memory, essentially, right? So the shared bandwidth to memory. And so memory is attached to a socket, which means that all chiplets or cores within the same socket, so out of 2 sockets, will have uniform local memory access. But if your data is sitting on a different socket, then you will have slower access because your cores are on one socket and then memory is sitting on another socket. So essentially, memory latency and bandwidth will depend on on your computation and memory locality. So to get best performance memory-wise out of these, you want to use the flag -CPUs per task 8, which will ensure that all threads in a single task will stay inside the same NUMA node or inside the same chiplet. And that will give you, best memory performance. So if you want to fill an entire an entire node run, well, all 192 cores, then you want to combine this flag, CPU per task equal to EAT, with this flag, and that will make sure that everything is organized into 24 tasks, and then each task is bound to a specific chiplet, and that will give you the best performance. Now, if we go to GPU nodes, things are somewhat more complicated there. There are on each GPU node there are 48 cores, and 1,100 gigabytes of memory. But there is just one socket with all 48 cores, organized into 6 chiplets, so the same number, 8 cores per chiplet. But there are 4 NUMA nodes. So NUMA nodes don't align perfectly with chiplets. So this makes it a little bit hard to give a single number you should use for the number of CPUs per task. So essentially, if your job is memory bound, you want all your threads to be in a task. All your threads in a task to stay within a single NUMA node. So in that case, you might want to try the flag specifying 12 CPUs per task to bind all tasks, all threads inside, all threads inside a task to a single NUMA node. But you might also want to try to experiment with the flag CPUs per task and set it to 8. So that might give you, depending on the code, depending on your memory usage pattern and how much you use a GPU, that might give you better performance or maybe not. So, I mean, really depends on the runtime circumstances. So there's no single answer. Now, there are 640 GPUs on the cluster, so 160 GPU nodes with 4 H100 cards per node. So these are much faster than the older generation GPUs we used to have on CEDAR. So unlike on CEDAR, one big difference is on FIR, you must specify the GPU type. So you can use it. You can do this either using the flag GPUs per node or just GPUs, and then specify the type and then the number of GPUs either per node or total per inside your job. So the currently 4 GPU types are supported. So there's you can use a full H100 GPU card with 80 gigabytes of memory, then I'll just say H100, or you can use one of the 3 available MIC partitions. So essentially each GPU is partitioned into 8 pieces, and you can use up to, into 8 pieces, yeah. And you can use up to essentially, you can use a MIC partition up to the size of 3G. So 3G means you can use 3/8 of the total compute power of a GPU. So I'm going to talk about this in much more detail in a few slides. So for jobs then that can utilize full GPUs, you will use one of these flags. So either GPUs per node equal to H100s and number of GPUs per node, right? Or the total number of GPUs, H100s, that will be inside your job. These will be, if you utilize full H100 cards, these will be built at 12.2 RGU, so-called reference GPU units. And if you're not sure what these are, essentially because we used to have a large number of different GPU types and they have different speeds, we came up with a single unit, measurement unit to measure your usage. If you search here for RGU, you will find the explanation and what that RGU unit translates to on actual clusters. So the problem is that the vast majority of codes will not be able to fully utilize an H100 card, which is really a problem because each one of those GPUs costs roughly $25,000 US. So if you're running at, let's say, 10% efficiency, or I don't know, 3% efficiency, then obviously you are wasting a lot of compute power. So why a GPU might not utilize, why a code might not utilize a GPU efficiently? There are many reasons, but the main reason is because the computational problem is just too small to saturate to GPU. So you can also run into bursty GPU usage patterns. For example, there are many serial paths in the code in between the GPU kernels, and these serial paths just drag, the performance so that GPU kernels do not run too often. Or maybe there's just too much compute on a CPU-bound compute on the host for, I don't know, data pre-processing or some other data manipulation. Perhaps your code was just not written efficiently, so that you have overhead from too many kernel launches. The computational problem might be inherently memory bound instead of compute bound. So you're just ending up shuffling a lot of data, and maybe there are some problems shuffling this data, with memory access, disk access, etc., and so on. So many problems, many reasons why your code can potentially be inefficient on a GPU. So that's why we highly recommend that you study GPU utilization of your code. So how can you do this on FAIR? So the best way to do this is to go to a job monitoring portal, but unfortunately right now it's not yet available on FAIR. So the team is working on it, and I've been told that it will come at the earliest, it will come towards the end of September, most likely in October. So for now, you can use portals on NIBI or Rockwell, but of course, these will be only showing GPU utilizations for jobs that you run on NIBI or Rockwell. But that's one option currently. So you can take your existing code and try to run it not on FAIR, but on NIBI or Rockwell, and use their portals to study GPU efficiency or GPU utilization of your code. So another option, theoretically, would be to use the GPU performance counters to profile your code, essentially, right? So while your GPU code is running, there are some metrics being collected, and then these metrics can be later be used by an NVIDIA profiler. Unfortunately, also, currently, the GPU performance counters on FAIR are disabled. They're disabled by default, and one of the reasons why they're disabled by default is because they represent a security reason. So if a GPU is shared by several users in Mix, for example, then those counters could expose things like memory access patterns, instruction throughput, and so on. So we're currently exploring whether this could be done on FAIR or not. They are also disabled on NIBI. On Narwhal and Rockwell clusters, currently GPU profiling is possible, but it requires disabling so-called NVIDIA Data Center GPU Manager, which collects metrics for the portal. And then if you disable, then these metrics can actually be collected for the profiler. So I have a slide on this in a couple of minutes. So at the moment, the only option on FAIR is if you want really to profile your code on FAIR, is to attach to an active running GPU job using things like srun-job ID. So if you pass this flag to currently to srun, where you reference the job ID is going to be a currently running job ID, then you can open a shell inside on a compute node which is currently running your job, and that way you can run various profiling tools like PS or TOP or HTOP. In this case, what I'm suggesting is you can run tools like NVIDIA SME, and that will give you real-time GPU utilization of your code. So here I have a couple of functions that actually much simplify this. So what these functions do is essentially once you start running a GPU code on FAIR, it starts running, just run SQ to make sure that your code is running. Then what this will do, it will grab the first, so it will use SQ to list all your currently running jobs, and it will grab the very first job in this list, and it will attach to the job, and then it will run NVIDIA SME tool only once. So if you want to run it continuously, like for example, refreshing the output every second, you can use this function, right? So this function will simply write NVIDIA SME in a loop every second, so that you can see real-time GPU usage. So when you do, you will see an output like this. It's all text-based inside the terminal, and there are two numbers that you want to pay attention to. So here's the GPU utilization, right? So in this example, it's great. So the code is running very efficiently, showing 100% GPU utilization, and then also GPU memory usage, right? So in this case, I'm using an entire H100 card. So here there are no MIG partitions. I'm using just the entire H100 card. And as you can see, out of the 80 gigabytes available, I'm using 76 gigabytes, which is actually pretty good, right? So eventually, you want these numbers to be similar to what you see on the slide. Now, I already said that you can also do this on NIBI because NIBI has exactly the same H100 GPUs. Actually, the timings on FAIR and on NIBI and to the cycle to millisecond, I got exactly the same timings for H100 cards on NIBI and FAIR because the hardware physically is, the GPU hardware is exactly the same. So here's how you would do this on NIBI. In this example, I'm just using my own GPU code that I wrote in Chapel. I mean, the details don't really matter. So the important thing is that I have a job submission script, and then I submit my job asking for, in this case, I'm asking for an entire H100 card. Here I submit my job, And one thing that I have to remember is that in order for these monitoring to be efficient, you want your job to run for at least 10 minutes. So I tried to run it for 4.5 minutes, and that actually was not long enough to gather these metrics for the portal. So at least 10 minutes. And then once your job finishes running, you simply go to the portal on Nibi, and then you log in. You go into the job stats and look up your job, and this is what you will see, right? So again, two numbers that you want to pay attention to: GPU utilization and then GPU memory usage. So as I said, in a few weeks, we'll have a similar portal on Fur, but right now it's not yet available. So another option is to use the a profiler tool. So here is an example of using a profiler tool for a GPU chapel code running on Rockwell. So here, one thing that I did was I actually, instead of running the Insight Profiler GUI on the same node that is running my job, what I did is actually separated the profiling, actually, running the job and profiling, and then looking at the output of the GUI profiler in a separate desktop connection. So here I run the code in the first part, and then I run it as part of the interactive job. Here I disable the counters so that these counters actually will be available to monitor, well, to the profiler, right? And then I essentially ran the code. So here I ran the code and I enable tracing of CUDA calls, and all tracing, all profiling information went into this file, well, actually into this file with the .ansys wrap extension. And then in a separate, so after my code finished running, in a separate connection, I went to the Jupyter Lab on Rockwell, and then I started a desktop and then opened the profiler, and that gave me a nice graphical interface where I could actually see information for my code. So again, this is not available in Fur, and the main reason it's not available in Fur is because the GPU performance counters are currently not enabled. Whether they will be enabled or not, I don't know. It's still currently being discussed. So if your code GPU utilization is not good, let's say less than 75%, what can you do? There are essentially three options. So first, you can scale your problem to fill the scale the problem up. So compute a bigger problem, right? To fill the GPU, but that could be tricky, right? It's easy to see, well, just, take a bigger grid size and that will saturate the GPU. That might not be the case. That might work or might not work. So again, you should really check GPU utilization. Another option is to use a MIC partition. So next slide, we'll talk about that. And then, of course, you can also take a code and just run it on CPUs. Don't ask for GPUs. So MIC partitions, I already mentioned them. So roughly half of all GPUs on Fur are partitioned into MICs, which is a proprietary NVIDIA technology to statically split H100 cards and E100 cards as well into smaller partitions. So there are 8 partitions. One of these on a GPU, one of these is used for managing the MIC instance, and then the other 7 partitions are actually used for compute. So our setup is such that there are 3 partitions available. So essentially 1/8 of a compute, 2/8 of a compute, and then 3/8 of a compute, right? With 10, 20, and 40 gigabytes of GPU memory available. And so basically you treat these as standalone, standalone GPUs with their own computer capability and then their own memory size. So usage is going to be built accordingly. If you're using just half of the card, then instead of 12.2 IGUs, it's going to be 6.1 IGUs, and then smaller numbers for smaller MIC instances. So one important thing to keep in mind: do not ask for multiple MIC instances in a single job, simply because on the same GPU, it's not supported in our Slurm config. So on a single GPU, if you want to run multiple codes, GPU codes, then use MPS, and that I have in the next slide. So if you wanted to use multiple MICs inside multiple GPUs, that is not across multiple GPUs. That is not, unfortunately, possible because currently MIC does not offer support for data transfer between different GPUs on a node over NVLink or NVSwitch, right? So different GPUs, the 4 GPUs on a node, they are linked by NVIDIA's proprietary NVLink connection, but MICs cannot, unfortunately, use it. So another thing that you should keep in mind that graphics APIs are not supported on Mix. And then there is also a big caveat on doing graphics on H100s, which I'll mention in a few minutes. So details for Mix, again, all links in these slides are clickable. So, but unfortunately, I have to enable to click on a link. I have to make it smaller and then not full screen, and then it will take you to documentation. So MPS is yet another proprietary technology from NVIDIA to allow sharing of a single GPU by many processes. And we have documentation for this, so I won't spend much time on this, but essentially here you'll be using an entire H100 card and then launching multiple GPU codes on that card, and you can launch up to 48 what is called MPS clients, so basically GPU codes utilizing the same card at the same time. So for visualization, it turns out, and actually I didn't know that until a few months ago, that the H100 cards, they are GPUs, they are server class cards that are not designed for graphics. So what it means is that they don't really support graphics that well in principle. And I'm not talking about MIG partitions that don't support graphics at all. I'm talking about the entire H100 card. So it turns out that out of how many thread controllers you have on H100 card, so that number is different. On our cards, I think it is 66, but I'm not 100% sure. But basically out of, let's say, 66 thread controllers on a GPU, only 2 can support graphics pipelines. And when I say graphics pipelines, I mean OpenGL and Vulkan applications. So what this means in practice is that if you try to do rendering on a H100 card, it will work, but it will work incredibly slowly. So actually, out of curiosity, I just tried it, and essentially it runs on roughly the same speed as a GPU on my laptop, right? So it's clearly a waste for a very expensive GPU card. So instead, what you want to do is there are several options. The best solution, in my opinion, is to just use CPU nodes for visualization. So when you're talking, so here we're talking about visualizing very large data sets. And your data set is probably already partitioned, or maybe it's a structured grid data set, which doesn't really need to be partitioned. It's done automatically in visualization software. But the point is that in order to visualize a large data set, you want to load it into memory. Let's say you're processing and numerical simulation where each time step is 80 gigabytes of data, right? A single time step is 80 gigabytes of data. So that in principle, you cannot load on a single node because, well, sorry, on a single core, because that will just overwhelm the bandwidth for a single core. So what you want to do is you want to do this in parallel. So to load it, let's say, onto 128 CPU cores. So that will take, I don't know, 20, 30 seconds to read the data in parallel from Blaster. And then the data is already now sitting in memory in parallel. It's partitioned among those 128 CPU cores. And it turns out that you can actually very efficiently use the same CPU cores in software for rendering, whether it's ray tracing or rasterization. So tools like ParaView and Visit actually support this really well. And for production visualization, this is much preferred to doing rendering on a GPU. So if for some reason you still want to do GPU rendering, then there are some options. So one of the options is to use AMD GPUs on NIBI, and they have unified CPU and GPU memory, which actually is supposed to make it very fast for rendering. So I still need to do some benchmarking, hoping to do this today or tomorrow of visualization on those AMD nodes on NIBI. But that's one of the options to keep in mind. So for interactive access, I almost have no time. I want to leave some time for questions. So almost the last slides for interactive access. We have roughly 10, I mean, that number varies with time, but we have roughly 10 nodes in the interactive partitions. So with a maximum runtime of 3 hours. So use Salog to submit jobs to those to interactive nodes. And of course, this is useful for visualization, for debugging, testing a code, etc. We now also have Jupyter Hub on Cetus. So there is a link here, jupyterhub.fur.alliancecan.ce. Will take you to this page. So already logged in this morning, but if you do it the first time, it will ask you to log in using your Alliance account. So do this with multiple factor authentication. And then now you can ask for some amount of resources. So let's say I'm going to ask for, I don't know, I'll just like 3,600 megabytes of memory, 1 CPU core, the debug partition, and then no GPUs. And then for user interface, I will select Jupyter Lab. So that is now it is starting a Slurm job. on the cluster, interactive Slurm job, and then inside the job, it will start once the job started, it will start a Jupyter Lab server, and then it will connect from the browser to the Jupyter Lab server, and then I will have a number of options here. So one of them is going to be open a remote desktop, which is really, really useful if you want to run some graphical applications. We also plan Open On Demand for the cluster. So Open On Demand is a different way of, so it's an alternative to Jupyter Hub. But right now, I don't have a timeline, so probably next few months, hopefully. I don't really know what services Open On Demand will run, but it will be, yet another way to do things interactively and graphically on the cluster. So here my job has started, and as you can see, one of the options, so I can start a Python notebook, for example. I can, so here's a Python notebook. Discard, yes, I can start a RStudio here if you want to run an R code interactively inside RStudio. And then another option is to start a desktop, which is what you would use if you want to do if you want to run graphical applications remotely. So here it starts this desktop, and then I can open, for example, a window, and then I can load a ParaView module. Let's see if this works. Load ParaView, and then okay. So okay, I will need to look into dependencies, but yeah, I will have to. Okay, I think already it's just a warning, right? So let's see. Okay, it loaded ParaView 6. All right. So this was installed just last night, and I have not had a chance to play with it. So I don't know whether this will work. Actually, the first time I tried ParaView 6 on the cluster. So let's see if it works. And then if it works, we'll actually open a graphical. Great, yeah, it works. It just opens the graphical window right inside my desktop session, running inside an interactive job on the cluster. So yeah, so I should also mention that other clusters also have graphical interfaces, but they're different. So somewhere is Jupyter Hub, somewhere is Open On Demand, and here I have the links to those services. So very quickly on FurCloud. Currently, FurCloud is not yet available, so the team is planning to make it available towards the end of September. So right now, all allocations from the RUC 2025 remain on Cedar Cloud. So that means that if you just go to the familiar interface, OpenStack interface on Cedar, log in, you will see your usual allocation there. But at some point in the next few weeks, that will be automatically transitioned into the FurCloud. So the FurCloud, once it's available, there will be an announcement from the lines, and also there's this page that lists the currently available cloud instances. So as you can see, Cedar is available, but Fur is not here yet. So at some point, Cedar is going to be replaced by the FurCloud. And I think I'll just stop here. So here is a list of summary bullet points. So essentially, Fur is ready for production now, but not all services are ready yet. So FurCloud, the portal, the most important things are coming in the next, Cloud First portal, hopefully in the next few weeks as well. And biggest changes are scheduling. You have to recompile your code. Make sure you do, if you're running a CPU parallel code, study efficiency, not efficiency, study parallel scalability of code. So how well it works, let's say, using 4 threads per task, 12 threads per task, and so on. And then, of course, when it comes to GPUs, make sure you investigate the GPU efficiency or GPU utilization of your code.